All right, guys, so once we have these substituted benzenes, what do we do with them? So, well, we end up doing more reactions, unfortunately. Okay, so, but they're not too bad. We're actually going to recycle them. The only difference is we need to know where on the ring that these groups go. So, there's two concepts I'm going to walk you through. One is activators, deactivators, and then the next one is going to be directors. So, let's talk about activators and deactivators first. So if you have a benzene with a group on it, like a methoxy group here, then it's going to cause reactions. So like you might react it with bromine and FeBr3. And so with excess bromine and FeBr3, you're going to see reactions, lots of substitutions going on. And so if you see lots of substitutions, that means that this is very active. So it's a strong activating group that's making the benzene want to substitute. So this is a good activator. On the other hand, if we see a group on there like this nitro group, and it's resulting in no reaction, then that's the opposite of an activator. It's called a deactivator. It means that the ring is not really looking for substitution because of the effect on the nitro group on it. So, sort of a drag. This nitro group is like the friend that never wants to go out with you when you feel like going out. Okay, so yeah, so that means that methoxy groups are activators based on just looking at the reaction. You see that it's very, very active for substitution. But the nitro group is a deactivator. Nothing wrong with not wanting to go out, by the way. I'm just saying sometimes one person wants to keep you in, and anyways. Okay, so there's a spectrum of how much a group is activating or deactivating. By the way, my friends always complain I like to go out too much. So, all right. So I'm an activator for sure. Here are groups that are strongly activating, okay, like me. So these groups like to add to the benzene ring. Okay, if you take a look at the trend with all these activating groups that I've circled, they are all electron rich. They have lone pairs. And so these lone pairs can donate electron density in. Let's just take this one as an example. See this lone pair here can be donated into the ring, and then it can be put onto the ring in various spots, or you could just resonate around the ring as well. So anyway, these all have that property of donating into the ring by resonance. Now notice that they're also electronegative atoms. Oxygen and nitrogen tends to be electronegative. And that means that it should be pulling electrons out of the ring toward itself, right? But the inductive effect of pulling out is outweighed by the resonance effect donating in. So oftentimes the resonance effect will outweigh the inductive effect. Now, in terms of donating groups that aren't as good as those, they're close though. We see these are definitely electron donating because of this O, and that O looks very similar. But this group here will cause some of the electron density to go the other way. Instead of into the ring, it'll go the other way into this carbonyl group. So in that case, you still have some resonance effect still that can go that way, but it's also spread out by this carbonyl group. So these are less activating. They're called moderately activating, whereas these are all called strongly activating. Okay, so there's some differences there. So with our groups, they're not really, they don't have lone pairs, so they can't be donating in by resonance, but they do donate in because they have electron clouds, and those electron clouds can be pushed into the ring by induction. So this can only be donating by induction. Now with halogens, it's a little bit confusing because they have lone pairs, so they can donate in, but they also tend to be more electronegative, like fluorine, for example, so they can inductively pull out. So they're electron donating by resonance, but they're deactivating because they are pulling away due to induction, so due to their electronegativity. And the reason why these electronegativity is more important for these, rather than O and N, which are really electronegative, is because of the effect of the resonance. So if you look at what happens when these do donate in through resonance, is they develop positive charge. And that's not as favorable for these halogens. And that's not as favorable for halogens to have this positive charge on something electronegative like that. But because it can technically donate in by resonance, these are just sort of mildly deactivating. So they're just barely deactivating. All right, these groups are moderate deactivators and electron withdrawing. So what features do they have in common? So these are what we call electron withdrawing groups. And they're pretty moderate. That means they're pretty good at electron withdrawing. So if we zoom in on one such one, like here, this ketone, so basically acetophenone, we're going to see this effect here. So all of these have an carbonyl group or some kind of sp2 kind of carbon on the ring, okay, or even sulfur. You know, all of these guys have this feature that the electrons can be pushed out of the ring, and not just one pi bond, but you can have, you can have it delocalized around the ring to lose some of that pi electron density. Okay, so these are all going to have the effect of electrons leaving the ring. So that's why we're calling them electron withdrawing groups. Now the really deactivating ones are things like nitro groups. It turns out nitro really deactivates. So if you take a look at it, you can see why. This can pull out of the ring. Okay, and then here, this can't really accommodate that because too many bonds to the nitrogen, but you can see by induction, because it's positively charged, it's pulling by induction. It's just sort of pulling the density towards itself, away from the ring. And here too, by induction, because of all the halogens, which are electronegative, it's just having an effect of pulling density out of the ring. So these are very strongly withdrawing. That's why we saw Friedel-Crafts didn't react with nitro groups on the ring. It's no reaction because they're very deactivating. So our summary here is electron donating groups. You should recognize that they have lone pairs. So this is a very common one, is phenol. So if you see benzene ring with phenol, it's electron donating because it can go into the ring. Electron withdrawing groups tend to go out of the ring. So if I had like some kind of a carbonyl group, these tend to go pull electrons out of the ring. Our donating groups are activators. They make the ring want to do substitution. And then withdrawing groups are the opposite. They tend to slow down a benzene ring for substitution. So I would love if you guys would take a minute then and just look at different groups and just work through. Give me some examples of a strong activator, moderate activator, and a weak activator or mild activator, and then also a mild deactivator, a moderate deactivator, and a very strong deactivator. And maybe just practice writing a few down and just ask yourself, is it strong? Is it donating group, withdrawing group? Is it activator or deactivator? Okay, maybe just start with that at first. Okay, so now we're going to talk about electron donating and withdrawing groups again, but we're going to look at the effect of that on synthesis. So I'm going to look at this benzene ring substituent or group, and I'm going to ask you, is this an electron donating or electron withdrawing group, and how can you tell? So I would say that you want to draw in your lone pairs. So this is a donating group. And so, because I can tell by the lone pairs, it's going to donate in toward the ring. Okay, this is an activator. So first, electron donating group tells me it's an activator. And this reaction here tells me I'm going to add an NO2 group, right? It's NO2+. So I'm going to add that to the ring, but where do I add it? I could add it here, 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 or here, right? And by symmetry, these two positions are the same, and these two positions are the same. So there's really only 3 unique positions to add the NO2 group. take a look at this reaction and what it's telling us. It's telling us that certain positions are more favored than others. So the para position, where it's the opposite side, that's really favored, 67%, but then I also have the ortho position also favored. The meta position, though, is a very minor product. So why is that? Well, this has to do with some analysis of resonance. So let's take a look at that methoxy group and see the effect of it donating electrons into the ring. So this is why it's called an electron donating group. It's donating by resonance. I can draw resonance structures showing that the negative charge due to the lone pair can be concentrated on different carbons via resonance structures. So I'm just pushing electrons onto a certain carbon, or making a pi bond and pushing them down here, or pushing them over to here. So through resonance, you can see that there's a spreading of that charge. And what that does is it helps us explain why at certain times the ortho carbons react or the para carbons react. And that's why we see para and ortho substitution, is because when benzene acts as a nucleophile, the negative parts of that nucleophile are what react. Okay, now let's see what happens with this kind of group, nitro. Did we say a nitro group? Do you think that's electron donating or electron withdrawing? Well, hopefully you guys said it's electron withdrawing, okay? And that's because of the effect of this nitro group. When you draw it out, it can actually have resonance away from the ring, okay? And that makes these positions here, more positive. Now, the benzene, though, acts as a nucleophile in all of these addition reactions, substitution reactions, right? The benzene attacks. Well, it can't attack if it's positive. So the only spots left where it's not positive by resonance are these meta positions here. See how those are never positive? So that's why we see a great abundance of meta product when we have a withdrawing group, is because those are the positions that are more nucleophilic, simply because we have resonance structures where they're not positive. Okay, but para and ortho positions are positively charged, so those carbons cannot be attacking the nitro group from this additional nitration reaction here. Okay, so the basic idea is I have benzene, but I already have a group on there. I have to tell if the group is going to be withdrawing or donating. If it's donating, I get para and ortho, but if it's withdrawing, I get meta as my major product. Now, what group do I add on second? That depends on what's here. This is my nitration reaction, so I'm adding a nitro group, and the question is, where do I add it? So we just solved that when you have a withdrawing group, you are going to add to the meta position for subsequent groups. All right? So that means that electron donating groups are ortho-para directors, and then electron withdrawing groups are meta directors. Okay, so it's good to remember that, and remember why that is. We did the little analysis with the charges. Okay, so here's a summary. Activators or electron donating groups are ortho-para directors, and deactivators are electron withdrawing groups, and they are generally meta directors. The only exception to all this are halogens. Halogens are slightly electron withdrawing by induction, but then they're electron donating by resonance. And so the induction part makes them deactivators, but the donating part makes them ortho-para directors. So it's a little bit crazy. I don't know why halogens have to be so difficult, but so they're like 1 foot in each camp. Okay, so our goal is you want to be able to look at a substituted benzene, and based on what group is on it, you want to tell, is it an activator or deactivator? And then, is it an ortho-para director or a meta director? And notice there's a trend. Activators tend to be ortho-para directors, and deactivators tend to be meta directors, except for halogens. Halogens are technically ortho-para directors. So let's apply this, okay? And you can use the chart until you get used to it. So for this one, predict whether the ring is activated or deactivated. So I see a nitro group. You probably know by now, but this is a strongly withdrawing group, so that means it's a deactivator. So electron withdrawing group, that means it's a deactivator. Is it an orthopara or meta director? Well, as a deactivator, it's usually going to be a meta director, unless it's a halogen. So I'm going to say it's going to be a meta director. So if I want to add another group on this ring, let's say I use BR2 in the next step, then I'm going to add it in the meta position here or here. So it's going to be one of those two spots. Okay, so go through and do the same analysis for me for each of these, and we'll go over them in a few minutes. All right, guys, so for part B, I'm looking at this group, and I see that this is an sp2 carbon, so I actually see electron withdrawing as well. So when you see a carbonyl there, it's electron withdrawing. So same thing, it's a deactivator, and it's a meta director. For this one, it's a halogen. That means it's inductively pulling out, so this is a weak deactivator. But it's got resonance donating in, so that's an ortho-para director. So that's our exception. It's hard. It doesn't fit the trend. Now for this benzene, I've got this whole group. So I need to think about this group. I can't really donate in, right? So there's nowhere to go there. But I can pull out there. I can pull the density out. So that is going to mean that this whole group here is electron withdrawing group, technically. Okay, so I think they're trying to fool you with this nitrogen. The nitrogen would have to be right here in order for it to be donating. But in this position with the pi bond here, it's sort of like a carbonyl group. So this is an electron withdrawing group. So that means it's going to be slightly deactivating, and it's going to be a meta director. Okay, so hopefully you guys have a sense now of whether you have resonance donating into the benzene ring or resonance taking density out of the ring. You have a sense of induction is something pushing in electrons into the ring by induction or pulling out. So you know, practice thinking about those concepts and activating versus deactivating and ortho-para directing versus meta directing. Okay, so for this problem, we are looking at predicting whether this molecule diazepam, or also known as Valium, we're going to see if it is deactivating or activating, and is it an ortho-para or meta director. So let's sort of analyze this molecule. So here's my benzene ring, and so I want to know what is the effect of the group attached to it. So I think you guys can see, based on a similar analysis we did previously, that we are going to have withdrawing from this ring here. So this whole thing right here is considered an electron withdrawing group as far as this benzene here is concerned. This is drawing electrons away. Okay, so that means that probably I'm going to have meta director. That this group here is a meta director if it's deactivating the ring, and that means that groups are going to want to come onto these positions here, get substituted right here. That's meta to this group. Now that's for this ring out here. We also have a benzene ring here, so there are substituent effects here as well. So if you take a look, maybe in a different color, I've got this that donates into the ring, so I could have ortho-para in these positions. I already have a group that's para, so I won't have anything there. So it's possible I may have some substitution here or here, but here I have 3 groups already, so I'm not going to be able to generate the aromaticity if I try to add another group here. So I probably will add it here instead. And I don't believe that's in the answer key is the effect of this benzene, but yeah, this group technically would be an activator for reaction on this ring, and this position would be the most likely as an ortho position to get reacted because this is an activator. But it's only mildly activating because of the effect here as well. So this lone pair isn't completely committed into going into the ring. It's also being pulled this way by the carbonyl group there. And then you could also argue that the benzene ring here could technically be pulled out that way. So this is actually withdrawing this way, but it's donating this way. It's a little bit more complicated to talk about this ring. As far as this ring is concerned, though, which is what the answer key talks about, is this actually is pulling density out, so meta director as far as that ring is concerned. All right, so let's say you have two groups on the ring. So now let's think about where would the bromination occur? Would it occur here or here, which are equivalent spots, or would it occur down here, where these two are equivalent? Okay, so let's try to figure that out. To do that, we look at which group is more activating. Is it the methyl group or the nitro group? So you should know that our groups are inductively donating into the ring, so this is going to be a stronger activator. Therefore, it will also be a stronger director. So this will determine where the bromine will go. So since this is an electron donating group, it's going to tend to be an ortho para director. So I'm going to look at the ortho and para positions. Here's my ortho positions and here's my para position. Para position's already taken up by the nitro group, so that means I can just add a bromine to the ortho position. Okay, so here's bromine right here. All right, great. Okay, and adding bromine on the other side is the same thing. It's equivalent because it's a flat molecule. Why don't you guys try the second one then? So this nitro group, this means that nitro group will be added. So then I look at the stronger of the two. This is way more donating than the methyl group is. So I'm going to add the nitro group here. So I hope that makes sense to you guys. Because this is a stronger activator because it's electron donating into the ring. And by donating into the ring, I make those ortho-para positions more negatively charged. But I already have something para, so I can only add to the ortho position at this point. Let's identify which positions are more likely to undergo substitution then. I've got the most activating, so it's got to be right here at the para position. For part B, it's this one, so let's see, it's a donating group, so that's going to be ortho, that's going to be this position as well. All right, and then why don't you guys try C and D? Okay, so for C, this group is the most activating out of all of them, so we're going to add to this ortho position here. And then for part D, this is a withdrawing group, and if you're not sure why it's withdrawing, I recommend drawing these out. You guys can see now it's going to pull electron density out of the ring. So that means this is a withdrawing group, so it's going to be meta here or here.